Okay, baru 37 orang je masuk ni. Okay, harap semua dapat masuk. Because today we're going to continue on liquid extraction, which is a very important. And you need today's skills to answer or to solve the problem regarding to LLE. Okay, so you're going to use graphical method to solve for the problems. Okay. All right. So let's say 41 of you. Okay. So I believe that you have done some revision regarding to the previous topics, okay, because you're going to have a short, not a short, 1 hour online quiz that will cover for chapter 1, chapter 2, and chapter 3, okay, which is your mass transfer for chapter 1, distillation for chapter 2, and then liquid extraction for chapter 3. Okay. All right. Okay, dah masuk dah 44 of you. Okay, Muhammad Ishra, Muhammad Hadi Syafiq, you boleh switch off you punya mic dulu, unless you want to say something. Okay. All right. So let's recite Kitab before we begin. Bismillah. Ar-Rahman. Yeah. Okay, I'm going to start sharing with you on the based on the slides that we have. Okay, we're going to continue on the second part of liquid extraction lecture. Okay, so today is a very important part because you need to know how to use graphical method to solve the problem. Okay, I'm going to share the screen. Okay, new features here. All right. Share the screen, include computer sound. Okay, on the screen. Okay. So I'm going to go through the notes that you have before, which is the notes for the class notes for the liquid extraction. So please, I've shared with you the ebook on this particular course. So please read the ebook, okay? So actually that is considered as your textbook actually, okay? Since you cannot buy the textbook, I've given you the old version of the textbook, okay? But the content is about the same, so please read the textbook to understand much better. Don't rely on the slide that you have here, okay? So don't rely 100%. So you need to have extra knowledge, extra understanding based on the book that you read, okay? All right, so in the last class, okay, we have learned regarding to the principle of LLE, okay, and you have to know that LLE depends on the solubilities between the liquid components, okay, and they need to be separated, all right. So you are given the concept where you need to know which one is called solute, which one is called solvent, and which one is called carrier, okay. So the solutes are the components that you really needs to separate from the solution. Okay, so normally you have your solutes plus your carrier in the solution, and they need to be separated. Okay, so your interest is on the solute. Okay, so because you have you want to separate your solute, okay, you have to select properly the types of solvent that can extract your solute from the solution that you have. Okay, so your solute must be soluble to your solvent, but your solvent is not soluble in the given solution. Okay, so this is just you use the solvent to extract the solute. Okay, and then in the last class also we discussed a little bit regarding to the differences between distillation and extraction. Okay, the most clear differences that you have is about the heat energy that is needed for distillation but not in the liquid extraction. Okay, and both are in liquid form. If you can see, for distillation, it works under due to the difference in boiling point to separate the components. Okay, so you have a binary mixture for your distillation. You need to have difference in boiling point in order to separate the components that you have in a mixture. Okay, but since you don't need external energy for liquid extraction, so you are focusing on the solvent that you use to extract the solutes. Okay, so when you look at this, okay, extraction is based on the solubility of your solvent to your solute, but distillation is based on the difference in boiling point of the components that you want to separate. Okay, so when you look at the operating cost, the operating cost for distillation process is much expensive compared to liquid extraction. And then if you look for the sensitive material, so you need to consider the temperature or the operating temperature that you use for the separation process if you're dealing with the sensitive materials. Okay, so you might prefer to use extraction process to for the sensitive or for the heat sensitive materials. Okay, so these are the solvent key points that we have discussed. All right, solubility, chemical reactivity, viscosity, and availability. Okay, okay, this is the last slide that we have discussed in the last class. Okay, so this is the process flow diagram of liquid extraction. If you look at this figure shows you we have multiple stage of LLE, okay, or liquid extraction, multiple stage. So because you have multiple stage, you have stage number 1 labeled as 1 here, stage number 2, number 3, until stage number N. Okay, if you're dealing with multiple stage, okay, you start with your extract with the symbol of V1 and your solvent as Vn plus 1, because you don't know how many stages that you are dealing with here. Okay, so we just assume the last stage will be N plus, will be N, and the label for the stream is Vn plus 1. Okay, again, let me remind you, we are only dealing with liquid and liquids. Okay, so this symbol V does not represent vapor. Okay, this is just to separate the symbol so that it's easy for us to use the symbol to represent the symbol for the calculation. But you need to understand the symbol V1 also represent liquid phase, Vn plus 1 also liquid phase. Okay, L definitely for liquid phase. Okay, but for liquid extraction, we use for the feed L0, and then for the raffinate Ln. Okay. All right, so this is a process flow diagram. If you were to label or to sketch the schematic diagram for the multiple stage liquid extraction, you're going to use V1, Vn plus 1, L0, and Ln, and then you need to label. This is your extract, your solvent, your raffinate, and your feed. Okay, so in the book, or sometimes you can refer to the video, they represent the heavy phase and light phase. Okay, the heavy phase represent the feed, okay, and the light phase represented by your solvent. Okay, so if you were to flip this diagram 90-degree, okay, if you want to flip this diagram 90-degree, all right, clockwise, all right, so your L0 and your V1 will be on the top of the diagram, and Ln with Vn plus 1 will be at the bottom of your diagram. Okay, so I've shown you before. Okay, let me close this one. I've shared with you the diagram. Okay, let's look at this. Okay, so you can see here heavy phase in, light phase in. Okay, so this heavy phase in represent your feed. Okay, your feed, or you can label it as L0. Okay, so this is how the equipment looks like in the industry, or maybe in our lab. Okay, if you go to our lab, if you have the chance to do the experiment, okay, so this is how the equipment or LLE equipment looks like. Okay, you have heavy phase is fed from the top of the column, all right, and then it flows downward because it is heavy. And then the light phase, which is your solvent, or the symbol that you might want to use is Vn plus 1, will be fed at the bottom of the column. All right. Since it is light phase, it will flows upward. Okay. So you can have countercurrent flows take over in the column. Countercurrent flow take over in the flow, or in the column, sorry. All right. So again, let me tell you this. Heavy phase in is L0. Light phase in is Vn plus 1. Okay. And then you have light phase out for the outlet, or your product that you have. So this is your extract. Okay, your extract. And then you have heavy phase out. This is your raffinate. Okay. So if you look at this, you have 2 inlet stream and 2 outlet stream. Okay. So your heavy phase, or your feed and your solvent, will be mixed in the column. Okay, and it will mix using the turbine that we have, or impeller that we have in the column. Okay, so that is to make sure that we have a good mixing between the heavy phase and light phase, because we know from the theory that the light phase, or your solvent, must be soluble in your solute. You have your solute inside your heavy phase here. Inside your heavy phase, you have your solute and your carrier. Okay. Only solute will be attracted to your solvent. Okay, because your solvent is soluble in your solute. Okay, but the heavy phase or the solution that you have here is not soluble in your solvent. Okay, so only your solute is attracted to your solvent. So that's why it will flow upward, and this is the light phase out where you collect your extract. Your extract will have a higher solubility of solute in your solvent. So this will be your product that is rich in your solute and your solvent. Okay, at the bottom part is the rest of the components that you collect from the heavy phase. That include your carrier. Okay, so your heavy phase consists of your solute and the carrier. Solute will be attracted to your solvent and will be collected at your extract. Okay, and the carrier will be collected at the bottom of the column, which is considered as the heavy phase. Okay, so a good mixing must be provided in order to achieve a good separation process. Okay, and then in the last lecture, I did mention about when you have to calculate the percentage of recovery of A. Okay, recovery of A or recovery of your solute. So you calculate the recovery of your solute based on what you have from the feed and then what you recovered here, okay, at your extract. Okay, the amount of the extract that consists of your solute, all right, you're going to look at the differences that you collect here. If more solute is collected at your extract, so the recovery is more than 50%, okay? Whereas the rest, which is not recovered, will be collected at your raffinate, okay? So remember, when you label this, okay, please, when you listen to this math lecture, do take some notes, okay? Do take some notes and make some label on the diagram. So that's easy for you to understand. Okay, so let's look here again in the slide that we have. If you have any question, just switch on your mic and then you can say, you can ask me question, yeah? So, okay, look at this part, percentage of A being removed or being recovered, they are the same thing. So when you talk about A being removed or solute being removed, solute that you have here exists originally, initially in your feed. Okay, when it's mentioned about removal of solute, so we talk about remove to the extract position, yeah, to the extract stream. Okay, then if you look at this, all right, if you look at the differences, the flow rates of solutes, okay, look at the formula below. Okay, so L naught multiplied by XA naught is the flow rates of the solute in the feed. Ln multiplied by Xn1, okay, so Ln here. So actually Ln multiplied by Xan, yeah, you can present this as Xan so that you don't confuse with the symbol, all right? So L naught multiplied by Xa naught because you have Xa naught. Here, Ln multiplied by Xan. Okay, so this is the flow rates of solute in the raffinate the flow rates of solute in the raffinate stream. Okay, so this raffinate represent the excess. Only little bit of solute will be recovered at this stream, but majority of your solute, which is attracted to your solvent, will be collected at your extract. Okay, so the difference between L naught XA naught minus Ln XAN will give you the amount of the solute at the extract. Okay, and then divide with the original flow rates or the initial flow rates of your solute in the feed. Okay, when you multiply by 100%, you get the percentage of A being removed, okay, or percentage of A being removed from the original feed stream. Okay, so this amount represents the amount of solute, okay, in the extract being removed from the feed. Okay, so we are looking for the highest percentage here. Okay, maybe 90%, maybe 80%, 70%, or maybe 99% to have a good separation process. Okay, so to have a good separation process, remember, you need to select your solvent properly. The preferential of your solvent to the process is very important. Okay, so the solubility of your solvent to your solute is very important in order for you to recover or to remove your solute from the process. Okay, all right. Okay, so this is the first technical part that you need to understand. Okay, since we are dealing with three components, okay, or three substances, okay, which is A, B, and C. All right, so let's present A to be your solute, B as your carrier, C as your solvent. Okay, carrier is needed actually, okay, to make sure that the process or the separation process occurs smoothly. If the composition is very concentrated, it's very hard to do the separation. Okay, so you need to dilute your solution, okay, in order to achieve the good separation process, in order to extract the solute easily. Okay, remember the contact between your solvent and your solute is very important to separate the solute from the solution. Okay, so the solute can be any important substances that you are interested to have. For example, I've given you in the last class, okay, we have example here, okay, you need to separate your solute based on the solvent that you use, okay, all right, and the solute is actually a combination or a solution that consists of your solute and your carrier. So you need to separate one of these, okay, based on the solvent that you select, and then you determine which one is your solute. Okay, like this one, vitamin E. If you want to separate vitamin E from the vegetable oil, so you have vitamin E in vegetable oil. Okay, so this is one of the example. Okay, you have vitamin E in vegetable oil. For let's say you have palm oil. Okay, let's say you have palm oil, which is considered as vegetable oil. But in your vegetable oil, you have vitamin E inside. Okay, but your interest is just to take out the vitamin E from the vegetable oil. All right, so you want to extract vitamin E. You want to remove vitamin E from the vegetable oil. Okay, so what solvent can you use? Example given here is you can use propane. Okay, so you mix propane with the solution of vegetable oil and vitamin C that you have. Okay, and then you mix them. Okay, make sure a good mixing occur where you need surface area per volume is higher. Contact area between the solvent and your solute, okay, must be higher to make sure that vitamin E can be attracted to your propane. Okay, so by having that, okay, by having propane, okay, as your solvent, you can remove vitamin E from the vegetable oil. So propane plus your solute, which is your vitamin E, will be collected at your extract. Okay, will be collected at your extract. So your extract will consist of solute and the solvent. Okay, but in your raffinate, you have the rest of the carrier. Remember, I've shown you the flow, okay, where you consider that as your light phase product and heavy phase product. Okay, so this is how it works. So later, when you have your product or your extract, which consists of vitamin E and propane, so this product will undergo another separation process, okay, so that only vitamin E can be produced, or you can separate vitamin E from the propane or from the solvent. Okay, so now let's continue. Okay, first technical parts that you need to understand is where you use graphical method to solve the problem. Okay, we need to know how to read the graph. Okay, because we are dealing with three substances. There are two types of graph will be given to you. Okay, one is with the three-dimensional axis. Okay, and another one is two-dimensional axis. Okay, so the two-dimensional axis only consists of y-axis and x-axis. They are the same actually. They are the same. Okay. The only thing that this is two-dimensional axis, and then this one is the three-dimensional axis. For the two-dimensional axis, your y-axis only represent the solvent. Okay, only represent the solvent. All right. So the solvent components. Okay, and then for x-axis, it represents the solute. Okay, the solute. All right. So when you talk about this one, if you compare with the three-dimensional axis, so I think that you are familiar with the two-dimensional axis. If you were to have three-dimensional axis, okay, you have three peaks. Okay, peaks here. Okay, so this is called equilateral triangular diagram. And the left is right triangular diagram. Okay, both represent the same information. Okay, represent the same information. If you're talking about the same solution and solvent. Okay, if you talk about the same solution and solvent, they should be the same. They should be the same data provided in that particular graph. Okay, so let's learn how to read this graph. Okay, look at equilateral triangular diagram that we have here. Okay, Okay, look at this symbol A, B, and C. Okay, at the peak of the triangle, you have 100% of B. Okay, here you have 100% of C. ABC is the components or the substances that you're talking about in your process. Okay, so you have A, you have B, and you have C. Okay, forget about which one is solvent, which one is carrier, which one is your solute. Okay, just look at this one first. Okay, so this is the peak for A, the peak for the B, the peak for the C. Okay, now let's look at the peak of the B. Okay, if you have the peak of the B, this one represents 100%. Okay, 100%. Or you can have in the fraction number, you have 1. Okay, when you go down, so you go down like this. Okay, now again, look at this part. So this is the peak and this is the base. Okay, the base. Okay, all right. And then you go further downward, you have the peak and the base of the triangle. Okay, senang cerita, this is your peak of the triangle. This one is the base of the triangle. Base of the triangle. As you go up, as you go further to the top of the triangle, the base becomes smaller. Okay, the base becomes smaller. All right. The bigger base is called 0. Okay, 0%. Okay. When you go to the next step, so this is the base for the B. This is 10%, and then followed by 20%, 30%, 40%, 50, 60, 70, 80, 90, and 100%. Okay. So that is how you read B, or the coordinates for B. Okay, the percentage here represent, if you talk about fraction, that will be 0.1, 0.2, 0.3, 0.4, 0.5, and so on. Okay, now if you look at the A, okay, so this is your peak. So this is the peak of the triangle. Therefore, the base for the peak A is this base. Okay, all right. So the peak for A, so this is the peak for A. Therefore, the base is the line BC. Okay, so the peak is 100. So you just follow this figure. Okay, so you have 10, 20, 30, 40. So this is how you read. You follow this base. The reading is based on the base of the peak component. Okay, all right. So you read until you get this one is 80, this one is 90, this one is 100. Okay, so if you look for the C, so this is the peak. Therefore, the base for the triangular, for the peak for C is base BA. Okay, base BA. So to read the coordinates, okay, you begin with the 0, 10, 20, 30, okay, 40, 50, 60, 70, 80, 90, and 100. Okay. All right. Now let's look at coordinate M. Since you have 3 axes in this diagram, so you need to give the complete coordinates that represent the composition of A, B, and C at this particular point M. Okay, so you want to see what value that you have for A, you look for A here. Okay, A here, and then go for the base. Which one is the base? The base is BC. So you go like this. 10, 20, 30, and 40. Okay. So the value of A, coordinate A at point M is 0.4. So that's why we put 0.4. Comma, then you look for B. So what is the point for component B at point M? So this is B, the base is CA. Okay, so you go upward. So you have 10B, 20B, 30, okay, 30% of B, okay, at this point. 30% of B is 0.3. Okay, 0.3. Next, you want to see for the C. This is your C, which is 100%. The base is this one. Okay. So how do you know this is the base? It's very easy. You learned about your mathematics before, okay, where you need to know the height, how you calculate the area of the triangle. So you need to know the height, okay. The height and the base must be in right angle triangle. Okay, when you draw a line, okay, to consider the height of the triangle, okay, you need to draw a straight line between the triangle and the base of the triangle. All right, so that is how you look for these particular coordinates. Okay, so C is here 100%. So you just follow this part. Okay, all right, 0. The base, second base is 10, 20, and then 30. So 30. So this is the base for C equal to 30%. So your C now is 0.3. Okay. So this is the coordinates for point M. Okay. All right. So let's say we have a concept here. All right. So look at this. In this diagram, okay, in this 3D diagram or equilateral triangular diagram, you are given equilibrium curve. Okay, so these are equilibrium curve. All right. So this equilibrium curve, you have 2 layers. Okay, one layer is called extract layer. So it is labeled as extract layer. And this one is called raffinate layer. The middle point between the extract layer and the raffinate layer is labeled as plate point. Okay, plate point. All right. So this is the divider between the extract layer and the raffinate layer on the equilibrium curve. Okay. So when you talk about extract layer and raffinate layer, raffinate is your product, extract also your product. Okay, both extract and raffinate must have equilibrium composition. Okay, must have equilibrium composition. So when you go to the lab and when you want to take the sample of your extract, you're going to take the sample for your extract at the same time when you take the sample for your raffinate. So the raffinate and the extract sample will be taken at the same time. Okay, why do we need to have that? Okay, in order for us to draw the equilibrium curve, we need to have 2 points. Okay, we need to have 2 points. One point is from the extract sample. Okay, another point is from the raffinate sample. Okay, so if you look at this diagram, you have a dotted line here. A dotted line, and make it bigger. Hopefully it's okay. So you're going to have dotted line here. So this dotted line is the couple between the extract and the raffinate. When you take the sample, you take the sample, you in the lab, okay, in the experiment, you're going to take the first sample, and then you're going to take the second sample, third sample, and so on. That sample will give you one tie line, okay, to build your equilibrium curve diagram. Okay, one is from the extract layer, one from the extract, another one is from the raffinate. Okay, so this is the couple. The tie line is the couple during the sample is taken. Okay, so you have many samples until you have few samples here. The coordinates that you have for your raffinate and the coordinates that you have for your extract will be labeled in the diagram, okay, in the equilateral diagram or in the right triangular diagram. You can build the equilibrium curve. Okay, all right. So this is called tie line. All right, tie line. So the moment you take your extract, okay, you must take the sample also for your raffinate. So that will give you this particular point and that particular point, okay, to give you the tie line. Okay, so this is when you want to build the equilibrium curve based on the tie line that you have. Other meaning of the tie line represent the number of stages. Other meaning of the tie line represent the number of stages. If you were to have multiple stages, by looking at this number, the number of the tie lines that you can draw, you can say that you have 1, 2, 3, 4, 5, 6 stages for your process. Okay, 6 stages for your process. Okay, so please practice. If you were to practice, let's say I would like to know the coordinates for which part? The coordinates for the plate point. For let's say, okay. If you want to know the coordinates for the plate point, so look for the A. Okay, so this is the peak, therefore this is the base. So the peak is 3, 30, 40, between 30 and 40. Let's say 37. Okay, 37. Okay, so the value of A is 37. Okay, jot down. Okay, A is 37%, which is 0.37. Okay, let's say B. Okay, B, the base is CA. Okay, so this is the base. So you read from here 10, 20, 30, 40, 50. Okay, so the B is 50%. Therefore, it is 0.5. Okay, so if you want to know the C, if you don't want to calculate or you don't want to read from the graph, you can just use the weight fraction, which is to find your C should be 1 minus 0.37 minus 0.5. Okay, so your answer should be 0.13. Okay, so let's check from the diagram. So what is the C? Okay, so C is here, the base is here. So this is 10%. It should be more than 10% or between 10 to 20%. Okay, so logically this one should be what? 0.13. Okay, so that is how you read the composition fraction from the equilateral diagram. Okay. Now let's look at the right triangular diagram. Okay. So the value here is not the same as this one because this is for different composition, different components. All right. So if you want to read the coordinates for M, so this is the two-dimensional axis. Okay. So this is A axis. Okay. A at the x-axis. So the value is 0.3 for A. All right. And then if you look for C, it is about 0.2, okay, for the C. Okay, so if you want to know what is the fraction for B, you just minus 1 minus 0.2 minus 0.3, which is 0.5. Okay, so you get 0.5. So it doesn't mean that you need to have three-dimensional axis to know the three components that you would like to know the fraction. Okay, for the right triangular diagram, if you know two values for the axis, okay, you should know the third value for the axis. Okay, so the total value that you get here should be equal to 1. Okay, same thing here. The total value that you get here should be equal to 1. If you get more than 1, your answer is wrong. Okay? Any question? Kan tertidur pula, tak tanya soalan. Okay. So this is what we have. All right. So if you were to have two-dimensional axis or right triangular diagram, which one is extract layer? Which one is raffinate layer? So if you were to have a right triangular diagram, the extract layer represents the purple dotted line here. Okay, this is extract layer. All right, extract layer. So this is raffinate layer. All right, raffinate layer. Okay. All right. So if you want to label, this is called extract layer. The bottom part here is called the raffinate layer. Okay. So where is the plate point? The plate point must be between this purple line and the black dotted line. Okay, it can be somewhere here. Okay, it can be somewhere here. All right. So this is the equilibrium curve of the three components or three composition that you have in the process. Okay. All right. Next. So you can revise this. Okay. Now is the time for you to know where is the position of one liquid phase and two liquid phase. Okay. So when you have your composition lies on the equilibrium curve, it shows that your raffinate and your extract are in equilibrium. Okay, are in equilibrium. Okay, but if you have your phase, okay, in one liquid phase area, which is above the curve or equilibrium curve that you have, your composition is not in equilibrium. Okay, the sample that you collected is not in equilibrium. Okay, same thing with the two liquid phase. Okay, two liquid phase, it shows that your composition or the samples that you have taken in the process is not in equilibrium because they are not on the particular extract layer or raffinate layer or on the equilibrium curve. Okay, so When you want to label that which area is called one liquid phases or two liquid phases, for the right triangular diagram, it is about the same. So this area is called two liquid phase area or region. The one which is outside of the curve is called one liquid phase region. Okay, one liquid phase region. One liquid phase region, two liquid phase region. Okay, so this is sometimes important because sometimes you will ask to label your diagram so that you should know where to label your diagram properly. Okay, all right. Okay, I'm going to give you this part, okay, which is a very important part. So this is where you apply the theory to calculate, to solve the problem given to you in the questions, okay? All right. So I'm going to give you a break, 2 minutes break, and then you come back, okay? So you can have some drinks or whatever. 2 minutes break, eh? Then we continue. All right, welcome back. Okay. So let's continue on the graphical method of solving the questions. Okay. So today is very important topics, because you need to have this information before you can proceed doing the questions. Okay. Or else you don't know how to proceed, how to begin answering the questions. Okay. All right. So this is how it looks like. Okay. For the multi-stage liquid extraction. Okay, so I don't want to proceed with this one first. So let's look at the diagram that I've shared with you. Okay. So this is the diagram for the single stage equilibrium LLE. Okay, single stage. All right. So if you were to have a single stage, the question will not ask you to calculate the number of stages. Okay, the number of stages for the process. All right. So you need to calculate the number of stages for the process when you are dealing with distillation. Okay, so you have stages number 1, stages number 2, stages number 3. But for liquid extraction, you have 2 types of process that you can proceed with. One is called single stage, another one is called multiple stage. For distillation, for single stage, you call it flash distillation. Okay. For the multiple stage, you call it continuous distillation or fractional distillation. Okay. For LLE, you call it single stage equilibrium LLE, or you can have multiple stage equilibrium LLE. Okay. So read the question properly, whether you are dealing with single stage or multiple stage. Okay. So if you're dealing with a single stage, okay, you're going to label your stream. If you were to draw the schematic diagram of the process for the single stage, L0 always the feed stream. Okay, V1 is always your extract stream. Okay, and then since this is single stage, the next stage will be L1 for the raffinate and V2 for the solvent. Okay, so you can label L0 is your feed, which is F. Okay, L1 is your raffinate, which is your R, and V2 is your solvent, which is S, and V1 is your extract, which is E. If you rotate this diagram clockwise, you rotate 90 degrees, it will represent the column that you have in the lab. Okay, in the lab. All right, where L0 is called the heavy phase. L1 is also the heavy phase. V2 is light phase. V1 also light phase. Okay, L0 and V2 must be in countercurrent direction. Okay, so we're going to have single stage or multiple stage countercurrent contact with countercurrent flow. Okay, all right. So if you were to have a single stage, all right, so this is how it looks like. Hold on there. So just make the comparison first. Okay, so this is how you look at the multiple stage. Look here. Okay, if you were to have single stage, it's just like this. Okay, if you have multiple stage, you have this and that. Okay, this and that. So you have something in between, or the number of stages in between. Okay, all right. So let's see this single stage. Okay, for this single stage, right, the overall mass balance, okay, the overall mass balance, you can have the inlet flow equal to the outlet flow. Okay, in is equal to out. All right, and it should be equal to the M. Okay, M is the mixture, so that's why it is at the middle of the curve or inside the curve. Okay, so if you were to mix this L0 and V2, L1 and V1, okay, so you connect a line L0 and V2, L1 and V1, you get M. Okay, you get the M position. So take a look at the right triangular diagram. Okay, take a look here. L0, you draw a line between the point L0 and V2. L0 is your feed. Okay, let's make it bigger. Can we? Or later. Okay. So if you connect the point on your triangular diagram, okay, between the feed and your solvent, all right. So And then you're going to connect between your raffinate point and your extract point. The intersection between these two lines will give you the point M. Okay, the point M. Okay, so M also has a coordinates. All right, M also has coordinates. All right, so the coordinates is represented by the XAM, XCM. So this is what you have. The composition at point M is XAM, XBM, and XCM. Remember, we are dealing with three components. All right. So the first one is for the solute. The second one is for the carrier. The third one is for the solvent. Okay. So M also has three coordinates. L naught also has three coordinates. All right. If you were to have three coordinates, all right, if you know only two, you should know the other one. Okay, because we have discussed before that the total value that you get from the coordinate is equal to 1. Equal to 1. So this is how you look at the single stage. All right, so you just stop that position only. Okay, so look at this. The connection between V1 and L1. Okay, if you draw the line is called tie line. Okay, tie line. Okay, V1 and L1 is called the tie line. All right, V1, L1 is one tie line. All right, so if you were to have multiple stages, okay, I just look again to the multiple stages. Okay, how does it look like? So it looks something like this. Okay, so if you have multiple stages, you can draw more tie line. V1, L1, V2, L2, V3, L3, and so on. Okay, so that is where you have multiple stages. So same thing here, if you want to translate, if you can draw the line between V1 and L1, that is tie line number 1. If you draw V2 and L2, you can get tie line number 2. V3 and L3, you get tie line number 3. So if you can develop 3 tie line, meaning that you can have 3 stages. Okay, 3 stages. All right. So if you can develop 5 tie lines, you can have 5 stages. So you have to know how to develop the tie line. Okay. So now let's look at the notes that you have. Okay. Okay, overall mass balance. So this is single stage, very simple. So you are given 3 equations where you can play around. Okay, the flow rates of the feed plus the flow rates of the solvent will give you the same as the flow rates of your raffinate plus the flow rates of your extract, which will give you the total flow rates of the mixture. Okay, so if you were to go the mass balance on component A, you just multiply the flow rates at each stream with the component A. Component A is your solute. So this is solute at feed stream. This is solute at the extract stream. This is the solute. This is solutes at solvent stream. Solutes at the extract stream. Solute at the this is extract. Tidak. Macam pelik je ni. Oh, this is L1. L1 means dekat raffinate. Okay. So this is at raffinate. This is at the extract. They give you the mixture flow rates multiplied by the components of solute at the mixture. Okay, all right, and then you can get the other one. So please, okay, if you want to do the mass balance, okay, do the mass balance for A and then followed by C. All right, if you know how to solve for A and how to solve for C, then you know how to solve for B. Okay, you have three unknowns, three unknowns, A, B, C, enough to have three equations to solve everything. Okay, but you need at least two equations. Okay, you need at least two equations to solve the problem. Okay, so you are given many equations here, so you can separate this one. L0 plus V2 equal to M, or L1 plus V1 equal to M. Or you can have these two, right, equality that you have. All right, this one equal to that one, this one is equal to that one. So you have two equations already, right? And then you're going to have this one, okay, equal to this one, three equations. Okay, so you can get three equations from the overall mass balance. You get three equations for mass balance on component A. You get three equations for mass balance on component C. All right. Okay, so this is the steps involved. Okay. All right. Now look at the continuation of the, where is it? Hilang pula. Mana dia? Hilang dah. Oh, this one. Okay. So, saya nak tunjuk. Mana pergi ya? Hilang pula. Mana dia lagi? Hiding. Okay. Alright. Okay. Teknik. Okay, teknik. Okay, teknik. Teknik penting ya. Okay. So each time you have the information for your feed, okay, for your feed, for your extract, for your solvent, and for your raffinate, you should build your graph. Okay, what is important? Okay, what is important? Okay, so the most important information that you need from the question is the components of A and C. A and C. All right. So if you know the components of A and C, then you can label your L0. So remember that this is L0, which is your feed. It is not yet undergo the process. It is not yet undergo the process. Therefore, the composition in your feed shouldn't be in equilibrium. Okay, shouldn't be in equilibrium. Same thing with your solvent. Okay, same thing with your solvent. Your solvent still not undergo the process. Okay, therefore it can be outside of the equilibrium curve. All right, so your solvent is not in equilibrium. Yeah. Now let's look at V1 and Ln. Ln is your product, which is called raffinate. V1 is called your product, also called this is called your extract. So your product undergo the process. Okay, your product undergo the process. If it is undergo the process and it is mentioned that it has they reach the equilibrium. Therefore, V1 and Ln must be labeled, must be plotted on the equilibrium curve. Okay, so if we assume that all samples taken from the extract and all samples taken from your raffinate reach the equilibrium, therefore the points for your extract and raffinate should lie on the layer or on the equilibrium curve. So this is how it looks like. Okay, V1 on the equilibrium curve, V2 also in equilibrium curve, V3 also in equilibrium curve. Okay, all right. So how to draw these things? Okay, so you proceed with the, if you want to know the number of theoretical stages for liquid-liquid extraction, we need to develop the way how we calculate the number of stages based on the tie line. Okay, because you need to calculate tie line. Okay, so let's say you need to begin with drawing your operating point. So this is the first step. Okay, let me remind you again. First step, label your composition at the 4 streams involved. Okay, feed, the feed stream, the solvent stream, the extract stream, and the raffinate stream. Label them first. Once we have labeled them, okay, you can draw a straight line, connect between your raffinate and your extract. You get one particular straight line. Next is to draw your feed. You connect your feed coordinate with your solvent coordinates. So you draw a straight line. The middle point represents the point M, which is your mixture point, and the coordinates is given by XAM and XCM. If you were to have B, that would be XBM. Okay, so how do you get this information? Why do you need this information? Sometimes you need to use the overall mass balance and the mass balance for the components that you have to solve the other unknowns. So you need to have this particular information to get your point N. Now, once you have this information, you have 2 straight lines produced. Now is the time for you to draw the lines where you can get the operating point. Okay, the operating point. So I always do something like Ultraman, can? Okay, so you cross, okay, something like this. Okay, one will give you L0 and Vn plus 1. Another one will give you V1 and Ln. Okay, so the cross-sectional point or the intersection between the 2 points that you have will give you the coordinates for M. Okay, next, if you connect the line between L0, if you connect the point between L0 and your extract, so, okay, and Ln with your solvent, which is Vn plus 1, you just draw a straight line from here to here and extend the line. Okay, extend the line. And then you draw from Ln to Vn plus 1, extend the line. Okay, so when these 2 lines intercept, you get your operating point. You get your operating point. Follow So kalau you terlepas benda ni, you akan terlepas dan tak faham. Okay. So why is this operating point is very important in your graphical method? This operating point is called also reference point. Okay, reference point. Okay, because when you develop your tie line, you're going to base on the operating point. Okay, now follow me. So you have V1, you have L0, you have Vn plus 1, and you have Ln. Okay. With the V1 and Ln, something like this, V1 and Ln, you cannot get your tie line. Awak takkan dapat tie line. Okay. So what you should do is, if you connect your V1, okay, you connect your V1 with the reference point or operating point, okay. You can see here, V1, V2, V3, semuanya connect dekat operating point. Dia converge. The line converge at the operating point. Okay, converge at the operating point. So when you want to draw the tie line, okay, if you were to have another graph below, okay, let's say, macam mana ya? Saya nak tunjuk. Okay, if you were to have another graph, it will support you the graph below. Okay, I will show you later. You're going to get this particular L1. Okay, L1. Alright. So apa yang L1 akan buat ialah, from L1, you connect with V1. Alright. You connect with V1, and then you extend the line from V1 to the operating line. Okay, from V1 to operating line. Okay. So dia begin macam ni sebenarnya. Okay. Alright. So you actually have another graph below here. So let me show you if I have one of the graph. Penting ya benda ni. Okay. Okay.
Alright, student.
Okay, this is one of the final exam questions that you might want to practice later. Any question ke? Sebelum saya proceed dengan lebih lanjut lagi. Okay, so you can get the questions from the final exam paper. Okay, so normally you will be given these types of graph. This type of graph. Saya tunjuk keseluruhan. Okay. Hold on. Okay. So actually, you akan dapat this type of graph. This type of graph. Atas dan bawah. Okay. So I just want to continue based on what we have discussed just now. All right. So you label your Ln, you label your L0, you label your V1. Okay. So this is the position of V1. So this is the position of V1. So how do we get the position of L1? Where is the coordinate of L1? L1 should be on the equilibrium curve. L1 should be in equilibrium curve because L1 undergoes the process. Okay, undergoes the process. All right. So it should be placed on this raffinate layer. Okay. V1, V2, and so on should be placed on the extract layer. So from the V1 that you have, you just draw vertical line downward until it reaches the second graph at the 45-degree line. So this is another graph that you will be given. Okay. So you just draw vertical line downward, and then from this 45-degree line, you just draw the horizontal line. Okay. Horizontal line to the right until it reaches the equilibrium curve down here. Okay. Then next you need to do is to draw the vertical line upward. Okay, upward. All right. So when you draw the vertical line upward, okay, you're going to get intersection between the second vertical line to the equilibrium curve here. Okay, well, let's say this is the point. So you draw downward from V1, draw downward, and then draw straight horizontal, and then draw straight
equilibrium curve to get
draw upward vertical line. So this will be the position of your L1. Okay, for your L1. From L1, what you need to do is to draw the connection between, you connect from L1 to V1. So when you draw L1 to V1, okay, so you're going to get one or the first tie line. Okay, the first tie line. Okay, so that tie line, all right, will be produced and will represent the first tie line. Okay, now from this, okay, you might want to look at where can you get your V2. Okay, so where can you get your V2? Okay, so you're going to get your V2 if you look through another example here. Okay, hold on. Saya pergi balik sini. Okay, from L1, tengok ni. Tadi kan kita dah ambil daripada V1. You just draw vertical line downward and then horizontal line and then it goes upward and then it's intercept at equilibrium curve. That is your L1. When you draw V1 to L1, you get first tie line or first stage. Okay, first stage. So the next thing that you need to do is connect your L1 to the operating point. Okay, connect your L1 to the operating point. When you connect L1 to operating point or develop a straight line between L1 and operating point, you're going to see another intersection occur at this position. Okay, as you draw the straight line, your straight line intercept the equilibrium curve here. Okay, so this equilibrium curve, the intersection point, will represent your V2. Yeah, V2. Okay, all right. So now it's time for you to label this point as V2. Now, how do you get L2? Because you need to draw the tie line between V2 and L2, and you don't have the L2. So what you need to do from V2, you draw a straight line downward until you reach the equilibrium curve at the bottom graph. Okay, straight line downward. Okay, and then draw the horizontal line. Okay, until it reach the equilibrium curve at the second graph at the bottom, and then draw upward vertical line, straight upward until it reach the equilibrium point, equilibrium curve. Okay, so when it's intercept, that point is called L2. Okay, L2. So you can draw the dotted line from V2 to L2 to represent the second tie line. Okay, all right. Next, you proceed again, same method, from L2 to the operating point. Where you draw the straight line, that straight line intercept the equilibrium curve here. Okay, so when it intercept at equilibrium curve here, that will be your V3. Dan dia akan bersambung-sambung sehingga selesai. Okay, bila nak selesai? Okay, so now mula semula daripada V3 turun ke bawah, straight line downward, horizontal line, okay, straight horizontal line, and then straight vertical line upward until it reach equilibrium curve, then you get your V3. Okay, daripada V3 pula, L3. From L3 pergi dekat operating point, dapatlah V4. Bila nak berhenti? You only stop when your L that you get, okay, I don't know which L, based on your drawing, okay, you get L1, L2, tiba-tiba L3 tu berada dekat sini, di luar. Berada dekat sini saja. Okay, so you stop. Okay, selagi dia berada di sebelah kanan, Ln, you will proceed doing that. Okay, dan kira how many tie line you can produce. But once it reach on the left of the Ln, you stop. Okay, on the left of Ln, you stop. Okay, then you calculate how many stages that you can have. Okay, so that will represent, okay, the number of stages if you were to calculate the number of stages for the multi-stage counter current LLE. Okay, so sama je konsep dia, macam you buat distillation. Let's say you get L1 here, L2 here, but L3 here. Maybe you get L3 here. Alright, meaning that ini stage 1, this one is stage number 2, but stage number 3 tak sempat sampai because dia dah melebihi Ln. Jadi your number of stages is 2 point something. Okay, 2 point something. How to calculate 2 point something? Okay, you measure everything. The length between L2 to to the last L. So let's say this is L3 dekat sini. Measure lah L2 sampai ke L3, berapa dia punya length. Alright. That will be the total stage. No, that from L2 to L3, the length is equivalent to 1 stage. Okay, but yours is not equal to 1, less than 1. So you just divide from L1, from L2, the length of L2 to Ln, divide by the length of L2 to L3. So you get the decimal number. So your answer should be 2 point something. Okay. So that is to cover, okay, the first method to solve the problem based on the diagram, based on the multi-stage theory that we need to use. Okay, all right. So any question? Senyap je ni. Takut saya awak faham ke tak? But you can refer to this this recording later, but you need to do something lah. Okay, so I will share with you the video on one of the example. Macam mana nak tutup ni? Okay, so I will show you, I will share with you on the problems. Okay, the video or the YouTube. Okay, so this is actually the YouTube.
All right, students, please.
Okay, so if you were given the questions, all right, on the liquid extraction, okay, the question looks something like this. Okay, so anyway, you need to understand how to solve the problem based on the theory that we have. Okay, I'll show you this video. I'll share with you the video to discuss about these things. Okay, so please watch this video. Okay, before the next class or before your tutorial class. All right, so that you understand a little bit regarding to how to solve the problem. Okay, all right. So I'll share with you in this. Okay. I'll put in this part, sample problem. Please watch this video. Okay. How to share the link? Control. Boleh. Okay. So please, I given you the tutorial questions. Okay. I need you to go to library to find the past year's questions. Past year's questions. So this is the tutorial questions that I've shared with you. Okay. Semua tutorial questions ni perlukan graph. Okay. So you need to go to the electronic question paper system from the library UiTM. So EQPS. Okay. So find the appendix. Okay. Find the appendix, and you need to print the appendix for you to practice. All right. So you cannot practice online something like this. Okay. So print the appendix. All right. So based on the appendix given, then we can do the questions. All right. So I want you to download the appendix for these particular questions. Question number 3, semua ada appendix, nampak tu? And number 4, number 5, okay. Right. Number 6, semua ada appendix. So for LLE, appendix is given. So you need to download and print the appendix. Okay. So download lah and then print lah more than one so that you can practice 2-3 times for the same questions. Okay. So we're going to continue on this. For group A, we're going to do the discussion during the tutorial. Okay. All right. Okay. All right. Any question? I stop sharing. Senyap aja kan? Tak nak cakap je. So can anyone ask any question? Is there any, do you think that this topic is difficult? Ke tak susah langsung? Okey je semua boleh buat. Download attendance list. Okay, 66 of you still in this session. Okay. So ada yang missing in action. So semua tu diambil kira ya. Bila you tak masuk kelas and then tak participate and then if you don't perform, so there's nothing I can do. Okay, so I do hope that even though you learn from the from distance away, okay, online, so at least you have you understand what's going on. Okay, if possible, try your best to understand, because remember, awak ni kan dalam semester apa, ODL, alright, but you are in engineering, so you need to have the knowledge. Okay, you need to have the knowledge, and then at the same time you need to have the practical, the psychomotor involved. Okay, so when it's involved, the practical, okay, I hope that you have the chance to be in the lab, okay, to look through the equipment and to understand much better on the operation or the operating condition or operating procedures that you need to carry out for that particular equipment. Okay, so we have in the lab a distillation column, we have liquid extraction column, we also have gas absorption column. Okay, so that is the time where you're going to learn better based on the psychomotor skills that needed by the industry. Okay, but still you need to understand the theory in order to for you to understand much better. Okay. All right. So I hope that you understand what's going on here, and then please do make some revision. Okay, and then read your ebook that I've given to you. Okay, so make sure that you ask questions if you don't understand, because this is skills. Okay, this is the skills, graphical skills that you need to have. Okay. All right, so I think that's all. If you don't have any questions, all right. That's all for today, and kita akan habiskan chapter ni by next week. Minggu ketiga. Minggu ketiga. So ini adalah minggu kedua. So minggu apa? Minggu 8 8, 9. 9, week 9, we're going to finish the maths lecture. And then 10, 11, 12, we're going to continue on the new chapter, which is gas absorption. Okay, 10 until week 12. And then week 13 to 14, you're going to do the special project for this course. Okay, so your lecturer will give you the topic for you to do the group presentation on the project. Okay. All right. So I think that's all for today. Thank you very much. Assalamualaikum.
Waalaikumsalam. Thank you, Miss.
Thank you, Miss.
Welcome.
Thank you, Miss.
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 Alhamdulillah.
Thank you,
Thank
Miss.
you, Miss.
You're
Thank you, Miss.
welcome.